Recording in progress.
Hello, David. Are we supposed to start at 4?
Yep, I'm here.
Okay.
They were waiting for Alexei, probably.
Yeah.
Or...
Oh, okay, Alexei just showed up.
Sorry, guys. I'm really sorry. This was a quick coffee break, and I got caught up with everything going on here in Texas A&M. Sorry, David. Good to see you.
Great to see you.
To advertise your talk after the plenary session and convince people to come from Philip's talk to yours, but it doesn't look like I was too successful. Good thing is that these talks are recorded, and so the audience will increase over time.
Yeah.
Thank you very much for being here online, on time and online, and let's start.
Yep, so I can perhaps share the screen then?
Go ahead.
You see my screen now?
Yes. Looking good.
Okay, so then let's start. So thank you very much, Alexei and Philip, for the nice invitation. So it's great actually to be at the Laser Physics workshop, even though it's it's a virtual format, but it's always good to catch up. So today, actually following Philip Russell's talk, I'm going to be telling you something a little bit different. And in particular, I want to touch on the role that optical shock formation plays when you self-compress pulses inside hollow core fibers, especially in the mid-infrared, where this effect is actually more acute. And let me take the pointer. So, and the motivation for this work is basically that if you want to do time resolve studies, ultra-fast studies in modern physics nowadays, it might be fantastic to have a light source that covers coherently all the spectral range from the UV down to terahertz. Because there is a lot of interesting physics, both in quantum phase and in molecular phase, that you can explore. For instance, in the ultraviolet, you have interband transitions, charge transfer, polarons, spin orbit couplings, and so on. And if you go to longer wavelengths, then basically you can study magnons, phonons, superconducting gap, and so on and so forth. But unfortunately, there aren't any available sources capable of covering this whole range at once. So the usual approaches to this problem are either nonlinear effects in bulk, basically taking an ultra-fast light source, which is either commercially available or customized, but with a limited bandwidth, because you don't have lasing transitions across all this entire spectrum. And then you use various nonlinear effects, for instance, in bulk, like in this work over here, where you basically focus your laser beam into a medium, like a gas cell or a crystal or any type of material that displays a nonlinear response. And then basically through various cascading nonlinear effects, you can broaden the spectrum. The problem is, like, of course, if you focus these laser beams onto something, the interaction length is normally restricted to the Rayleigh range, and therefore you need to put a lot of energy into this to make it work, because normally nonlinear interactions are fairly weak. So that's why the approach of choice for most basically non-laser experts is to go to a synchrotron facility, because there you can have any basically wavelength across this range with sufficient brightness to your experiments. But the price you pay for this is, of course, this is a building scale facility. You have to bring your laboratory stuff and equipment to, plan a campaign and bring it to the facility, rather than having the actual laser source in your own lab. That would be much more convenient. So a solution to this is basically using a hybrid system. And this paper was published like a couple of years ago, back to one of us, in which you use a hybrid approach. You have a light source, which perhaps is a laser combined with some frequency broadening system, like an optical fiber. And then you use this basically frequency broadened laser source to, in combination with different crystals, to cover different parts of the spectrum. And this is very nice because you can cover a multi-octave spanning range, but at the expense of having to switch between crystals. And this might not be a good option if you have to do, for instance, palm probe experiments between different spectral regions, and you have to mechanically switch between them. You can have instabilities, and this might be an issue if you want to deal with CP stable systems. So our take on that, to basically create a multi-octave light source that is coherent, delivers ultra-short pulses, and is capable of covering this whole range, is based on three basically state-of-the-art technologies. The first one is an ultra-fast mid-infrared laser, which is a laser that has been developed at ICFO, the group of Jens Wiegert. It's 3.2 micrometer laser, delivering pulses of 94 femtoseconds of duration at 160 kilohertz rep rate, and the pulses are CEP stable. So the carrier to envelope phase is controlled and stable. This laser is fantastic, but it doesn't really cover a large bandwidth on its own. So normally this is combined with a nonlinear crystal. In our particular case, we used a special mid-infrared crystal that was developed for this particular project, which has a very complicated chemical composition. We call it in short VGGSE. And the main features of this crystal is a Chi2 crystal, which is highly nonlinear and features a huge transparency window. So it really covers from the visible, you see it when it's half polished, it's actually reddish, from the visible all the way to beyond 16 microns. And you can AR code it, which is very interesting when you're dealing with high average powers. And this crystal was developed by our collaborators at the Cuban State University and the MBI in Berlin. And bridging basically these two technologies to go to the shorter wavelength range instead of going to the mid-infrared, they are these anti-resonant holocore fibers that Philip Russell told us about this afternoon. In this particular case, this single ring type that we also have seen, and it has been fabricated at the Max Planck Institute in Philip Russell's division. So let me tell you a few words how these fibers work, even though Philip already gave a fantastic introduction about this early this afternoon. So you have this type of structure in which the gray region, this is a scanning electron micrograph of a real fiber. Basically the gray region is silica glass, and the black region is empty space. And if you design the satellite capillaries with a wall thickness which is thin enough, they can actually trap light into the center, because the light cannot escape through these tubes, coupling to any modes into the structure, because there's anti-resonant. And this allows you to have extremely low loss. Actually, in variations of this structure, it has been already challenging the lowest losses that you can attain in any optical fiber. along with the broad transmission window, which is very interesting for ultra-fast studies. So you see here a simulation, finite element modeling simulation of the fundamental mode. You see a nice resonance here, which on a minus 30 dB scale, you barely see any light touching the glass. And this is very interesting because then the damage threshold is extremely high, which is also good for ultra-fast, high-intensity studies. And if you fill the fiber with something, like in our case, a gas, both light and matter are tightly confined, and they will be forced to interact over a long distance, which is not limited to the Rayleigh range, as I told you before. And last but not least, of course, because the dispersion of the waveguide is weakly anomalous, if you put a gas in away from electronic resonance, then you can have a pressure tunable dispersion landscape, which is pretty useful. And as I said, the broad transmission windows are extremely wide, but they're interrupted by loss-inducing anti-crossings between the core modes and most in the glass capillaries, which is something to be avoided in this case because not only cause loss, but also dispersion will be uncontrollable. Okay, so the scheme that we developed for this multi-octave light generation is fairly simple. So you couple the laser free space into a gas cell where 20 centimeters of this fiber are in. So there are reasons, of course, for these parameters to be like this. If you want, you can ask later. And when you fill it with argon through various nonlinear effects, you can get broadened the spectrum and a shorter pulse that can be then used in the mid-infrared nonlinear crystal, the BGGSE, to extend the spectrum further into the mid-infrared. So, but let's just concentrate in here because it's where optical shock effects really play a major role. So the way, physically, the way we broaden the spectrum coherently inside the fiber is through solid-on self-compression, because we have a high damage threshold, we have kernel linearity from argon, and anomalous dispersion from the waveguide. Therefore, we can have solid-on dynamics. So basically, self-phase modulation and dispersion can be balanced perfectly. In an ideal case, you could have a temporal solid-on, everybody knows about this, in which basically the shape, both in time and in the spectrum, doesn't change. So meaning that the solidon is actually the ground state of its own potential. But there are other solutions which are also periodical, but they change along the propagation, which are higher order temporal solidons, which undergo very complicated dynamics. And if you look carefully, when you have the initial pulse, you really create a temporal focus, then the pulse splits and do a lot of crazy stuff. But you get already a shorter pulse with a broader spectrum pretty much for free. And this is what we exploited in the lab. So you see here experiments in which you have the basically the temporal envelope of the output, the pulses at the output of the fiber at different argon pressures for a constant energy. And at the beginning at 15 bar, nothing much happens. So this is pretty much the duration of the original pulse, which is 94 femtoseconds. As you increase the pressure, you increase the nonlinearity. And therefore, the pulse gets shorter and shorter and shorter, as you see here. And at 25 bar, it reaches a minimum duration around a single optical cycle in the mid-infrared. And if you go beyond that, of course, the pulse becomes a mess because the nonlinearity is so strong that this temporal focus happens somewhere inside the fiber. And therefore, the subsequent propagation inside this fiber, which becomes highly dispersive, destroys completely the temporal structure of the pulse. If we look in the spectral domain, basically this is again the same data as before, but in the reciprocal space. You clearly see that at 20 bar we have just basically the spectrum of the light source, and when we start increasing the pressure, you see that the spectrum really gets massively broadened from the UV all the way down to beyond 5.5 microns. And to get insight on what's going on inside, we can model the system using a unidirectional field equation, which is Carrier resolved. And you see that we can get pretty good agreement with minimal tweaking, which is always good because now we can have access to the temporal dynamics inside the fiber, something that is not easily to do otherwise. And these are basically the intensity profiles at the output of the fiber. At 20 bar, you see pretty much nothing. So this is the input pulse. But as you increase the pressure, the pulse gets shorter and shorter, reaching a minimal duration of 3.5 femtoseconds at 30 bar, and at 35, as I said before, the pulse becomes already quite structured. But there is something interesting here. So if you look at 3.5 femtoseconds, it turns out that basically one single cycle at 3.2 microns is 10 femtoseconds, and 3.5 is less than half an optical cycle of duration. The question is, so you could say, yeah, but you're creating a massive spectrum, so it might be that the spectral centroid shifted to shorter wavelengths, meaning that the effective, the effective single cycle is indeed shorter. But thanks to this current resolved modeling, we can have the actual electric field corresponding to this intensity profile. You see an intensity peak of about 1 volt per angstrom, which is pretty strong. And if you zoom in the region of the spike, you see that half an oscillation of the electric field at the peak is indeed shorter than 3.5 femtoseconds, meaning that with this technique, we can generate sub-half cycle transients directly from the nonlinear dynamics without having to do anything else. And on top of that, if you look in the spectral domain, you see that in the UV, when the spectrum reaches there, there is a concentration of spectral power that starts to grow for increasing pressure until it becomes even comparable to the pump. So it becomes very efficient. And this is the result of a resonant transfer of power between a dispersive wave, which is a free-running wave on the opposite side of the zero dispersion wavelength, and the actual self-compressed pulse. And if they both phase match because of the dispersion, then there is an efficient transfer of energy, which is highly efficient and is widely tunable, as you can see here. What I wanted to tell you is, like, if you both look now at the temporal profile at 3.5 femtoseconds, or even in this simulation here, you clearly see that when the pulse compresses and reaches the temporal focus, it's extremely distorted in time. So there is a shock front. So basically, on the rear side of the pulse is actually getting much steeper than on the leading edge, and this is crucial for the dynamics. Why this is interesting? Well, if we think of the physics of physical shock events, right, in general, it turns out they are ubiquitous. So we have them everywhere. From in the atmosphere, we have angular bores, we have in liquids oscillations, we have in quantum fluids, like in Bose-Einstein condensates. We have it in optics. So this is interesting in nonlinear crystals, that you can observe this in the spatial domain, these shock waves. And they are very, very interesting because they really encircled a lot of very interesting physics. And at the same time, it turns out that nature seems to dislike them, meaning that they are very difficult to observe, because once you have a discontinuity in a field, nature tends quickly to regularize it. And it has different mechanisms, normally through dispersive interactions, like in the case of optics, it's going to be in the spatial domain diffraction, or in the time domain dispersion, and tries to release all this energy that is stored in this discontinuity through the emission of wavelets and the reconfiguration of the optical waveform. And this is actually what happens in optical fibers. This is a topic of very long standing. So this was already more than 50, almost 60 years ago predicted, and also very nicely analyzed theoretically in this paper, Anderson and Lysak in 1983. What happens theoretically, that basically when you have your initial Gaussian pulse inside a fiber, because of the nonlinear dynamics, the third order susceptibility, in which the main contributions are here. So this nonlinear polarization, and you have two contributions. You have the Kerr effect, which everybody knows about. So A is the temporal envelope of the pulse. So modulus of A squared, something proportional to its intensity, plus some additional term, which is proportional to the derivative of that term. And this derivative of that term means basically in the spectral domain that the intensity profile, so basically the intensity or the group velocity of this pulse becomes intensity dependent, meaning that the regions of high intensity will propagate slower than the regions of low intensity, implying that basically the trailing edge of the pulse can catch up after some propagation, as you see it here. And if this continues further, you will see that basically the variation so this derivative of the intensity with respect to time will become infinity. So you will have discontinuity, and the pulse will break up. So this is basically what happens when you have an optical shock front formed by a self-steepening. What is interesting is, like in this very simple formula here, there is a term that normally is overlooked, which is this dependence on the input frequency. I said it's overlooked because normally we operate in the near infrared where we have efficient sources, but now that we have access to a manifold of different laser sources, it turns out that operating in the mid infrared, where this term where the central frequency of the pump is going to be much lower, will enhance this effect, and this is actually important to be studied. And why am I saying this? Well, if you think again of the ultra-short pulse dynamics inside these fibers for the generation of these UV dispersive waves that were pioneered in the group of Philip Russell like 12 years ago in this paper here, and I took this, actually borrowed this from this paper. This is a simulation in which they just solve the generalized nonlinear Schrödinger equation, including both, including and switching off self-steepening. And what you see here, the first thing that you see qualitatively is like nothing really happens. in terms of spectral broadening. So the spectral broadening is in both cases the same. The compression length, so the length at which this spectrum explodes, which is the position of the maximum compression, remains largely unaltered. But of course, there is an increase in the efficiency of the dispersive wave, as you see here. And this is because this is a result of an increased, basically, amount of power that goes into the blue side because of the onset of the shock. When the shock is present, basically the blue part of the spectrum will be massively enhanced, thereby facilitating a stronger coupling between the self-compressed pulse and the UV dispersive wave. So we could say that in the near-infrared, the main effect of self-steepening is to increase the strength of the dispersive waves. If we now do the same for our experiments in the mid-IR, so these are simulations for our parameters, we also use 20 centimeters in our experiment. You see in the time domain, the pulse when self-steepening is off, the pulse also compresses in time, and you get around 17 centimeters the temporal focus, which is pretty symmetric, as you can see here. And you get this spectrally broadened spectrum, which does not extend much below 2 microns. And the main reason for that is basically the absence of the shock, the absence of self-steepening, as well as the presence of this band here, which is the position of the first order anti-crossing between the core mode and modes in the glass capillaries that I showed you before. So they completely disrupt the dispersion, leading to a concentration of spectral power here and also a disruption of the spectral power, and it's very difficult to basically jump over it spectrally. In contrast, if you include self-steepening, you clearly see that up to 12 centimeters or so, the dynamics is pretty much the same, but then the pulse compresses much more and generates this shock front here, leading to the emission of the dispersive wave that you can see it here as an interference pattern, because basically the dispersive wave interferes with the tail of the soliton and has a different phase. And nicely, the spectrum now will jump over this resonance and get to the UV where it gets concentrated. So we basically win compared to the near-infrared. We are winning all the NIR visible and UV part due to the presence of the optical shock. But we can compare this directly to experiments. So if we go to 35 bar and we plot basically the results of the simulation on top of the experiment. So the experiment is the thick black line. As you see here, when you don't have self-steepening, as I anticipated before, you have here this phenotype peak, which corresponds to the resonance, and you lose basically anything below 2 microns. So nothing is in there. Whereas when the self-steepening is in, you see a fantastic agreement, to my taste, with a simulation that doesn't have any free parameters. So it really predicts what's going on, even the amplification around the resonance. So basically, long story short, in this system, the onset of optical shocks, so the spectral fingerprints that they leave behind, are really crucial if you want to get a coherent spectrum that stands from the UV to the mid-infrared. And just to finish, once you get these short pulses, which are tailored inside the fiber, we can go straight into the Chi2 crystal, so the BGGSC, for the generation of for the extension of the long edge. And that we do via intrapulse difference frequency generation, which is a second-order nonlinear process in which basically 2 signals, so the pump and a given signal in the spectrum mix up, and there is a component of the nonlinear polarization which actually oscillates at the difference between these 2 frequencies, giving rise to the idler. And because both pump and signal are within the same bandwidth, so they belong to the same pulse, then the whole process is coherent. And I give you an example of what we obtained. So we characterize this in the time domain directly. So we measure the actual electric field by electro-optic sampling at 25 bar, and you see this kind of oscillation. So 86 femtoseconds, which is 2.5 field cycles at 10.3 microns. And now we can get the spectrum by Fourier transforming this, and this is what you see, which nicely fits the gap between, so it's reaching what the spectrum from the fiber ends, which is about 5.5 microns, and extends it coherently beyond 20 microns, even 40 microns, depending on the parameters. So basically, we can cover all the spectrum thanks to this extreme self-compression aided by the shock fronts inside the fiber. So just to conclude, I hope I've convinced you that basically gas field anti-resonant fibers are really nice tools for the control and the manipulation of ultra-short pulses, especially in the mid-infrared, where it turns out that optical shock fronts are really important, actually crucial ingredients that are always there, and you need to tailor them or take advantage of them properly to get nice self-compression dynamics and multi-octave spanning spectra that can be useful, phase stable, and so on. With this, I thank you for your attention, and I will take any questions you may have.
Thank you very much, David. And thank you for finishing on time. Even though we started 3 minutes late, we can give you these additional minutes. Let's see if you have questions. Maybe I'll go ahead and start with one. Just a basic question. Your shock waves form at the trailing edge of the pulse.
Yep.
Acoustic shock waves form at the front of the pulse. Yes. Water waves, like surface gravity waves, form steep fronts at the front. Yep. What is kind of the overall situation? Are most of these natural phenomena result in shock waves at the front? And is an optical shock wave special in this sense?
I think it depends. I mean, I honestly think it really depends on the actual physical system, because you can have pressure waves basically as they are formed, for instance, in the atmosphere or in liquids. That depends on the different pressures, and the hydrodynamics will dictate basically where this will happen. And normally this is in the leading front, if you want. So this is the shock front. Whereas here we can establish a formal analogy, but it's not complete because the physical system is different. So what's really happening here is like we are delaying with this intensity-dependent group velocity. We are delaying the peak of the pulse, such that the future can catch up, right? Mm-hmm. And so in my opinion, the main difference would be that one. So the difference in the physics of the actual formation of the shock front, which is good for us because it enhances the blue tail of the spectrum because of self-phase modulation. If this were to happen here, because there are other phenomena that basically enhance or steepen the leading edge, this will enhance the red part of the spectrum, so the long wavelength side.
Mm-hmm. Okay, thank you.
Welcome.
Anyone else? Let me ask another question, and then we'll continue. What is your feel or prediction how far down you can push the pulse duration? So you have demonstrated this single transient spike of the electric field.
Well, it really depends. So so we have seen the spectral fingerprint of that. So we haven't measured this in the experiments. We have measured that in the near infrared, for instance. 3 femtoseconds, where we have a single optical cycle. This we have measured, but not in the mid-IR because the bandwidth is so huge that anything along the beam path will distort it. So it's not very easy to compensate for the spectral phase distortion that the optics introduce in the mid-IR, especially when you have this massive spectrum going through. Just the window of the gas cell will disrupt it. So if you go to vacuum, you could do it, but it's tricky. So at some point, you will have a limit, which will be carrier shocking. So the actual carrier itself will break up. And this is something that has been observed in the terahertz range, which is a dislocation in the actual electric field. And that might be interesting, but I think it's really probably a fundamental limit, breaking the actual waveform itself.
Okay, excellent. Yeah, thank you so much. This is excellent work. I've been trying to follow it as much as I can. I'll be looking forward to this manuscript you list as in preparation. We'll see what you publish there. And let's continue to the next talk. Masayuki Katsuragawa. Masayuki, are you ready to share the screen?
Yes.
Here you are. Good to see you.
Yeah, good to see you. Thank you very much for giving me this kind of nice opportunity. So, just a moment.
We'll continue at 4 minutes behind schedule, which is perfectly fine. We'll still finish overall on time. Yeah. Yeah, we see your slides. Go to
Okay.
presentation mode.
Okay.
Perfect.
Okay.
Thank you.
Okay. Can you see my slide?
Yes, everything looks great.
Okay. I'm stopping. So, the title of my talk today is Optical Processes Tailored by Glass Plates. So, this work was done by Chiaki Owae, this guy, and Wei and Liu, this guy, and the Jian Chen, this guy. He's theorist, and me. So, basically, phase always plays a key role in optical processes, as light is basically wave. So the optical device which can control optical phase almost arbitrarily become a key tool in optical processes. So this is our optical device. We place transparent dispersive plate on the optical axis and change plate thickness a little bit. That's it. Very simple, but very powerful. Let me show you one example. Shall we assume 1 femtosecond transform limit ultra short pulses are incident to this optical device? So how do you think what happened after this? I think many of you imagined this transform limit ultra short pulses collapse quickly to noise burst like waveforms like this. So you are right, but partially. So here we plot peak intensity of output waveforms. So unity means the ultra short pulses are generated in the time domain. So as you imagine, if we increase plate thickness a little bit from there, so the peak intensity quickly down to the 0.2 or something. So something like this. But if we continue this plate thickness change more, so something like this, and we continue this simple calculation, then we found peak intensity was almost perfectly recovered to 96.8%. So is this accidental? So it's not. We found very similar recovery points, many recovery points in this way. And at the specific plate thickness of 3.734 millimeter, the peak intensity was almost perfectly recovered to 99.4%. So here we assume 5 spectral components with the spectral interval of 124 terahertz. The total bandwidth is 496 terahertz. So this bandwidth can produce 1.8 femtosecond ultra short pulses in the time domain. So for understanding this phenomenon more, we tested different cases. So next we tested 9 spectral modes, expanding almost 1 petahertz. Then this bandwidth can produce ultra short pulses having 850 at second part duration in the time domain. So this is the result. So the required the recovery points become the condition of recovery points become very severe, but still we could find several recovery points like this. And this specific plate thickness, the peak intensity was recovered to 93.1%. So as you can imagine, if we increase the number of plates more, so we can realize this kind of optical phase manipulation more freely. So here we tested a very simple calculation. So the spectral bandwidth was same as the previous one. This axis corresponds to the case when we employed just one plate, and this plane implies the case when we use two plates, the fused silica plate and sapphire plate. And this region correspond to the case when we use three plates, the fused silica plate, glass, and calcite. So if we use just one plate, the recovery peak intensity of waveforms in the time domain, the maximum was 0.922 when we change plate thickness from 0 to 12 millimeter. But if we use two plates, the maximum peak intensity reached 0.966 or 0.697. Sorry, 0.979. Then if we introduce three plates, so as you can imagine, the maximum peak intensity reach 0.995. By increasing the species of plates, we can control optical phase more arbitrarily. So what is the physics behind this phenomena? So I'd like to explain briefly. So now we are assuming very broad bandwidths, for example, 1 petahertz. So this transparent dispersive plate naturally include high order dispersion, something like this. Third order and fourth order amplitude C3 and C4, for example, are not non-negligible here. Then when we change plate thickness a little bit, these coefficients also changes simultaneously, but the change of speed are different among these. So this means even though we simply change plate thickness, we can test a variety of second order, third order, fourth order combinations. That means we can realize arbitrary dispersion form. So even though we very simply change plate thickness, there's still we can nearly arbitrary optical dispersion. So here I'd like to explain more quantitatively. Here we assume 5 spectral components like this. Then this axis corresponds to the phase. Here 0 to 2 pi. So the phase look very flat, but still, so this is arbitrary phase, optical phase. Then this optical phase has include the higher dispersion. Sorry, this optical phase can be reproduced by introducing up to 4th order because this optical phase can consist of just 6 spectral modes. So this amplitude of 2nd order, 3rd order, 4th order, C2, C3, C4 can be easily obtained by solving linear coupled equation, something like this. Then we have one solution to retrieve this optical phase. The coefficient of 2nd order dispersion, 3rd order dispersion should be, for example, this one. Here we just show 2nd order dispersion and 3rd order dispersion. So if the solution is just one, this optical device does not work so realistically. But to be very fortunate, the phase has a freedom of 2 pi. So there are many equivalent spectral phase like this, and any combination among these are equivalent with each other, so, something like this. But including the higher dispersion are different among these. So there are many equivalent solutions in the solution space. So when we change red thickness a little bit, this is a trace of this is a trace of 2nd order and 3rd order dispersion when we change red thickness. So as seen here, when we change red thickness a little bit, so we see many approximate solutions. So this is a physical mechanism why we can realize arbitrary spectral phase, even though we very simply change red thickness. And this physical mechanism is somehow related to the Talbot phenomenon, but this mechanism is basically different from the temporal Talbot effect. The temporal Talbot solution corresponds to this corner, this four corner. But what we found here is not only this corner, but also there are many approximate solutions exist in the solution space. Then the mechanism, the physical mechanism somehow analogous to the relationship between lattice and reciprocal lattice in solid material. Okay. Then we applied our optical device to one is to linear optical process, and the other is to nonlinear optical process. But today, I'd like to show you one example when we apply our optical device to linear optical process. This one, and this is a proposal. This is a conceptual idea proposed by Professor Ted Hensch almost more than 30 years ago. So his idea is something like this. So the first, he generated 6 phase lock spectral mode by phase locking 2 independent CW laser. Then by introducing nonlinear optical process, he generated 6 phase lock mode. Then he manipulated spectral phase among these 6 spectral modes by introducing this kind of mechanism. Then so he proposed, he suggested this system can generate sub-second pulse after-shot pulses. But this idea has not been tried yet. Maybe one reason is the idea is very interesting, but technically too difficult. So, but we thought if we introduce our optical device, which can arbitrarily or almost arbitrarily manipulate spectral phase, it will be very realistically work for this conceptual idea. So we tried in reality to realize this conceptual idea. So in our study, we generate 5 phase lock mode in the spectral domain. The master laser is just one laser, we call 3 omega. Then we introduce spectral divider, frequency divider. Then we generate omega and 2 omega. So very exactly by comprising phase lock loop. Then after that, we mix 1 omega and 3 omega, then generate 4 omega. Then also by mixing 2 omega and 3 omega, then we generate 5 omega. So something like this. All of these generation were done on the collinearly. So we, we did not separate any spectral components. So in that sense, the generation are very stable and very simple. Then after that, we introduced our optical device. We place transparent dispersive plate on the optical axis, then try to manipulate spectral phase among these 5 spectral components. So this is a photo of experimental system. The system is very complex. Then this is the simplest illustration of the entire system. This part we generate phase lock. This part corresponds to frequency divider. We start from 3 omega, 801 nanometer. Then we divide this frequency to omega and omega very exactly by making the phase locked loop. Then we generate 4 omega and 5 omega. Then after, sorry, we skip this part. Then we try to manipulate optical phase. Then try to generate arbitrary optical waveform in this case. So this part we manipulated amplitude distribution. The conceptual idea is basically the same as this one. Then this part we manipulated spectral phase. So the actual device structure is something like this. Then this is a result. So 1 omega, 2 omega, 3 omega, 4 omega, 5 omega. And the gray bar means the target. And the red bar, pink bar means the realized amplitude and phase. So here phase, sorry, target phase is blue dotted line, and the realized achieved phase is shown with error bar something. So from this information, amplitude distribution and phase distribution, we retrieved temporal waveform in the time domain. So S3. Then you can see a cosine-like waveform or sine-like waveform or sawtooth-like waveform in the time domain generated very beautifully. So then the pulse duration here was 830 attosecond in the time domain. Then so this is a waveform, amplitude waveform. So if we take intensity waveform, the pulse duration became 620 attosecond. So I think this pulse duration will be the kind of record because this is in the visible region. Maybe this pulse duration will be the shortest pulse duration realized so far. So anyway, so we could successfully realize the arbitrary optical waveform in the optical frequency region. And then this phenomenon is somehow analogous to the function generator in the electronics. Okay. Also, we have checked the reproducibility. So the reproducibility was not so bad. So here we show the magnified data of this plot or this plot and this plot. So the phase, the generated phase of 5 modes little bit fluctuated. They also phase manipulation is had some ambiguity, but still so we could keep the almost same temporal waveforms in the time domain entirely. Okay. So now we are trying to apply this optical waveform to control electron motion by shining the generated optical waveform to the scanning tunneling microscope. So, but we have not succeeded this study yet, but still trying to realize the control of tunneling electron by this optical waveform.
Masayuki, we are at the 25-minute mark. This is so exciting. I hate to stop you.
Okay.
Yeah.
Okay. I'm sorry. So this is summary. We have shown our optical device, and we have realized the arbitrary optical waveform in the time domain. I'm sorry. Thank you very much.
But can you go to the previous view graph so that we can see what you wanted to show? I don't. Can you go to the previous view graph? Yeah, this one. No, next one.
Next one.
Yeah, this
okay,
one.
So, yeah, this is just perspective. So what is
That's
possible?
in Japanese.
Yeah, if I'm sorry, I can't change language to English.
Okay,
So,
okay. Yeah, thank you.
Okay.
I wanted to make sure I'm not missing something exciting here.
Yeah.
Very good. Thank you. Other questions?
Hi.
Yeah, go ahead, Kai. Or do you want to ask a question?
Yeah, I want to ask a question. Hi,
Go
Professor Katsuragawa. Yeah, I have a question about very nice talk. Thank you. So I have a question about the stability of your scheme. So you are achieving some like 800 attosecond. So I'm wondering whether like this glass plate, if there is some vibration due to the airflow or thermal expansion or something, are they going to affect this stability of your this waveform generator?
So we have shown the experimental data.
Yeah.
So to measure to have this data, we needed more than 30 minutes. So maybe in the experiment there are some fluctuation as you pointed out, but still that effect is something like that. In this case, so in that sense, they're not so serious.
So you don't do any particular thing to stabilize your optics, right? You don't.
No, we did not apply any special control. Just we place the plate and change that thickness effectively. That's all.
And then a related question, the lasers you use are CW lasers, injection seated and external cavity diode laser. What is the typical line widths of these?
Line this be maybe tens of kilohertz.
Tens of kilohertz.
Because we lock that frequency to the external cavity. So maybe be very stable. Then we injection seeded that diode laser to CW high sapphire laser.
Yep.
Then typical power was around 1 watt or something.
Okay, yeah, beautiful work, and I'll look forward to any results from this electron control experiment.
Yeah, I hope so.
Yeah, thank you. Let's move to the next talk.
Yeah, thank you very much.
Go ahead, stop sharing.
Yeah.
And next talk will be given by Kai Wang. Kai, are you ready?
Yeah, let me share my screen. Just give me a second.
good hearing your voice, Kai. Feel free to turn on your camera, or I don't know, sometimes the Wi-Fi bandwidth is not good enough.
Right, I prefer not to turn on the camera because it will limited the internet.
Okay, turn it off then.
Yeah, I just want to make it smoothly.
Okay.
All right.
Go ahead.
Okay. Yeah. First, thank you, Alexei, and thank you, Alexei, for the invitation to give me this opportunity to present our recent work at this very nice conference. So my talk will be about this nonlinearity spectroscopy of mid-infrared, which we explored in the last couple of years. Yeah. This is the outline of my talk. So first, I will just remind you of something about this mid-infrared spectroscopy. It's basically we focus on this vibrational spectroscopy. So for molecule, there is a vibrational mode. The vibrational mode will have different, according to its symmetry, they are divided into different groups. Some of them, we think, according to the optical activity, is Raman active. The other one is IR active. So both is this IR and Raman spectroscopy can be used to identify these molecules according to their absorption signature. So Raman spectroscopy, many of us are very familiar with. But this talk I will focus on this mid-infrared spectroscopy. So mid-infrared basically according to wavelength, it's in the range of like 750 nanometer and 1000 micrometer. It's like a near infrared, mid-infrared, and far infrared. And for the molecule has different vibration modes. They have different this vibrational mode have different energy, so they are in the different region. Application of the mid-infrared light will be like identify the different chemicals and do some sensor, like an environmental sensor. And in our study, our purpose is do some biological imaging. So we are focused on this biological application. Also, it can be used in the fundamental research study, like a physics, chemistry of the molecule, and then some material science and the quantum information, and so on. So mid-infrared spectroscopy, and you may know that they have some limitation. The first, like we always say, like mid-infrared light, you cannot directly detect it with a silicon-based detector. So we have to use some detector like this. It has liquid nitrogen cooling or TEC cooling. And also because I mentioned we want to work on some biological imaging. So usually if you directly use the mid-infrared light, they will have a poor spatial resolution because wavelengths. And what's more is for the biological sample, for example, it always has some water. Water also has a very strong absorption for mid-infrared light. So it also limits the application of mid-infrared light in the biological study. This is a water absorption you may be very familiar with. So you know that mid-infrared light has very strong absorption for the water, but the water itself is in the visible light, it's a very low absorption. So for some standard mid-infrared spectroscopy technique is like Fourier transform infrared light. It's FTIR. You may know it's like you based on the interferometer and you measure the fringe, and then you do the Fourier transform, we get the signature of this absorption. And then our talk is, I will focus on the nonlinearity of the mid-infrared light. This is some nonlinearity of the mid-infrared light has been explored in many different ways. Like this one is you can use the microresonator to generate a broadband of mid-infrared light based on its nonlinearity. You can also use it to do some biological imaging. People actually tried it like with the mid-infrared light to illuminate some biological sample and then use a nonlinear crystal to convert it, scattering the mid-infrared light to the visible light, and then you detect it with a much simple silicon-based detector. And in the mid-infrared light, for the nonlinearity, mostly you are talking about second order or third order nonlinearity. So here is But for the second order and the third order nonlinearity, one of the most extensively studied technique is some frequency generation. They have a different scheme for this some frequency generation. Here is these two. One is like second order some frequencies, and the other is third order nonlinear. Third order is some frequency generation. Second order nonlinearity usually has a much higher susceptibility than the third order nonlinearity. But the signal usually is poor because most of the samples they have the symmetry, and the second order we cannot. Most of the sample due to the central symmetry, so the second order nonlinear signal is usually very low. So if you want to detect the signal, have a strong signal pattern, signal to noise ratio, people usually to do it on a surface or interface. This comes to this some frequency generation spectroscopy, which is already, as I mentioned, is extensively studied by the people in the chemistry and physics. They have the virus configuration, and they can use generate some frequency on the surface or in the interface, which give you a better signal to noise ratio, which is not be limited by the symmetry of this sample. So then I will come to our work. We also want to use this nonlinearity of the mid-infrared light. We want to use nonlinear spectroscopy. We want to use nonlinearity, and we also say we use the third order nonlinearity because we want to make this one much more general. So firstly, is like this scheme. So you will see that we first have the mid-infrared light, which will be unresonant with the vibrational state of the molecule. And then we have another near-infrared light, which is a probe field. And the probe's coherence built up by the first mid-infrared light, and then we generate a signal, which will be in the visible lines, consider the wavelengths. But here is the phase matching condition. You will realize for most of the material, they probably has a phase mismatching, because for most of the material, the refractive index will decrease as the wavelength is increasing. So this is limited the application of this technique. It probably has a very lower signal to noise ratio. But even though there is some material like water, this is a refractive index of the water. So you will see this water has the refractive index is much more complicated. And you can find some region and you can have a strong, we call SFG signal. And then somehow we realize that when we mix this mid-infrared light and the near-infrared light, there is also a difference frequency generation happens there. This nonlinear process, this is like an energy scheme here, and then you will see the first mid-infrared light will unresonant with the vibrational state, and then another near-infrared light will the probe, and then he also generates this difference frequency generation in the visible regions. And the better thing is for this scheme or for this nonlinear process, for most of the material consider their refractive index, you will find a situation or condition they will have this phase matching, which means they will give you much better signal to noise ratio. And then I will come to our experiment result. So we realize this thing and we try to explore this technique, this spectroscopy experimentally. The first one is what we did back at Texas A&M. So this experimental setup, and then we use a femtosecond laser amplifier, and then we have the OPA. We can get the wavelengths at center wavelengths of pulse. Pulse duration probably 100 femtoseconds. And what we studied the sample is we call it LDPE. It's just a low density polystyrene. It's just the plastic film we use in the daily life. So we will, this is a FTIR measurement and also a Raman measurement. So we will try to explore the vibrational mode at around 3,000 wave number, which is corresponding to the stretch mode of the molecule. So this is a result published a couple of years ago. And then this is a 2D spectrogram. One is time delay between this mid-infrared and near-infrared. On the other hand, is just a pump and the probe. And the y-axis is just the wave number of the signal. So you can see there is a signature about this in the spectrogram, which will also be corresponding to the vibrational mode of this LDPE film. And you also see there is this funny structure. This is probably some quantum interference effect coming from like a final resonance, or you can also probably explain it using the language of the Dirac state. And then, as I mentioned, we realized when the SFG happened at exactly the point, we also had a DFG signal. So we collected it and then we do this analysis. Still is a 2D spectrogram, and the x-axis is the time delay between the pump and the probe, and the y-axis I changed to the wave number, and also is offset by the probe field, so it's directly corresponding to the vibrational mode of this film. So you will see there is some difference. Firstly, because this is from the same film, same spot, and the spectrometer, the parameter is exactly the same. So you will see they have a little bit different signal to noise ratio and a little bit different structure. It's probably due to this nonlinearity property of this material. This is a thin film, and then we go to oil. It's a mineral oil. So in this experiment, in the figure C and D, we use a oil sample which is much more thicker. So in this case, you see these are totally different signal to noise ratio. This is almost exactly as we expected, because as for the SFG, as I mentioned, for the most of the material is like phase mismatching. So the coherent length of the material is pretty short. It probably just 20 micrometer or something. But for the oil, because the refractive index property, so most likely we can find a phase matching condition. So the coherent length here is much longer, so therefore it has enough signal. It has a much better signal to noise ratio here. And also, because this is using femtosecond laser, and so we can extend it to a time result spectroscopy. One thing as a demonstration we can study is still this decay of this vibrational mode. So the sample is here is still the LDPE. And on the figure A is a signal from the glass. It's from the DFG signal. Yeah, I should mention them both. Yeah, this is from DFG signal. So this signal from the glass most likely cross correlation between the two pulses. And then in the figure B, you can see that from both SFG and DFG, we summarize the signal from the spectroscopy as a total intensity and plot it as a function of time delay. And then you can see, compared with the signal from the glass, or compared with the pulse itself, you can see there is a tail. This tail is corresponding to the decay of the coherence of the vibrational mode. For the SFG and DFG, it might be different, because if you remind from the previous slide, you can see that the SFG and DFG, the signal still have a little bit different. We think the DFG may be excited more vibrational state, so it contained a little bit more information than the SFG, which makes them a little bit, there is some difference between them. And then the next, as I said, our goal is to do something for the biological imaging. So imaging, especially for the chemical imaging, because we want to take advantage of the mid-infrared light, which will be unresonant with the vibrational mode and help us to identify different molecules. So we do some demonstration of the proof experiment. This is an experiment done for using the DFG actually. Use the PMMA bead, and we put it on the LDPE, the film. So based on the spectrum signature, we did some data processing, and then we can identify the PMMA bead and also the LDP film. Okay. Another thing from this picture is you can see there is a spatial resolution. But these two figures probably could not show you that the spatial resolution from this DFG is really higher than this like the mid-infrared direct imaging. But on some other work, we have the demonstration. Here is another result. It's using it's the mixture of the PS and the PMMA. Here we still want to demonstrate the chemical selection property. Yeah, you can see the based on this spectrum, the property, we can see the PSB and also PMMAB. Okay. I want to mention that before we did the work, we realized another group from California, from Professor Potomat's group, they also published several papers, also based on the same energy level scheme. So basically, it's the same SFG signal, but they are using the picosecond laser. Their work is basically focused on the biological imaging. So he did some research. He compared this technique with the standard coherent Raman technique. And their conclusion is basically these two techniques probably is similar. They have the similar spatial resolution, similar signal to noise ratio, and so on. Yeah. So now I'll come to my conclusion. So right now we just experimentally we demonstrate this DFG and SFG signal based on this third order nonlinearity of the mid-infrared light. We also try to explore this potential of these two spectroscopy technique in this chemical imaging, and eventually will be studied for the biological imaging. And in future, yeah, we want to extend this work in some complex system, or maybe using some metasurface to enhance this nonlinear signal as well. Yeah. So I think I finished my talk. Yeah, thank you very much for your attention. Also, I want to this acknowledgement. This work is done basically by Jizhou at Texas A&M and also Wen Xuanyu at Zhejiang University. Yeah. All right. Thank you.
Thank you very much, Kai.
Yeah, for your attention. Yeah, thank you.
Thank you. Other questions? Very nice point about phase matching. That makes a difference between some frequency generation and difference frequency generation. Yeah, very, very well prepared and made point. Very nice. I enjoyed your presentation, Kai.
Yeah, thank you. Yeah, I think this DFG as SFG itself can be complementary to each other. So we probably can find some situation we can take advantage of both of this, this signal. And
what do you think about two-photon excited fluorescence? Is that going to be a problem? Because that would be a difference between some frequency and difference frequency generation. Some frequency is above all possible two-photon excited processes, and difference frequency can be in part masked by two-photon excited fluorescence. Yeah, in this diagram. You can see that. What do you think about that?
You mean the two-photon fluorescence from the near-infrared light? Yeah. So far the experiment, what I saw the result, I don't think the sample we use has a strong fluorescence. In future, it might be a problem because if really it happened, we probably need to change the wavelength of the near-infrared light. We don't want to excite it.
Yeah. When you use transparent films, there is not much fluorescence, but something biological can fluoresce when excited effectively. Yeah, at the green-blue single photon wavelengths.
Right. But in that case, I think the best solution is just change the wavelength of the probe field. But also, we should make a point that this fluorescence actually can be another technique for this imaging. If we can make a like this is made infrared light excited this vibrational state, and maybe another two photon process help us to resonantly enhance the fluorescence. It might help for the imaging as well, right?
Yeah. Nice work. Shall we move forward to the last talk of this session?
Of course.
Stop sharing.
Right, I will stop sharing.
And I'll share my screen because I'm the next speaker and the last speaker of this seminar. I'll try to be concise with my presentation and not abuse my powers as a chair of this session. I'll talk about biophotonics, at least that's the goal, using spectroscopic tools to study biological systems. I'll start by showing you some faces of people who have contributed to this work. Can you hear me well? Just to make sure.
Yeah, I can hear you.
Good. Many people have contributed, including generations of graduate students and postdocs and current graduate students here, and we always have room for more. The aim of this work is to basically add color to these sorts of images that show structure of various biological objects down to the size of single viral particles. But these are black and white cryo-EM pictures. We want to add color to them, and our route to adding color is Raman spectroscopy or vibrational spectroscopy in general. And our way of achieving nano-resolution is tip-enhanced techniques. So here's the scheme for tip-enhanced Raman on the left. We raster scan a sample with this metallized tip, plasmonic nanoantenna, and we record spectra from spots with a few nanometer spatial step. And it's by deciphering these spectra that we can get chemical information or color type of information for our images. And this is a technique that we learned a lot about from Volker Deckert when he visited here in the first year of COVID-19 pandemic. He's pioneered many of these tip-enhanced spectroscopic techniques, and he has taught us how to use them to look at viruses and other samples. In this example, tip-enhanced Raman spectroscopy is used to distinguish different types of viruses. And here, tip-enhanced Raman spectroscopy is used to study and sequence DNA. A single-strand DNA molecule is stretched on a surface and scanned point by point with half a nanometer step. So this is pushing this technique to the extreme. Half nanometer spatial steps coincide with the separation of the DNA base pairs, and we read the spectra and we decipher them and read out the code of life. And it was an experimental discovery that these plasmonic nanoantennas with a characteristic size of tens of nanometers can resolve spatial features on the sub-nanometer scale. The workings of these plasmonic nanoantennas are kind of similar to how a TV antenna works, even though there is substantial difference in physics. This is a famous Luthergus cup picture from the British Museum, and the colors here, green in reflected light and red in transmitted light, are due to the plasmonic effect. Of course, the artists back then did not know the plasmon physics. We do. We understand that when metal particles are used, you apply a field to them, you can pull electrons out of the surface and then make them oscillate back and forth if the applied force is periodic. You can also have propagating surface plasmon polaritons that can propagate for microns. It's quite a distance at these scales, propagate for microns along the surfaces of metals, provided that the surface is good enough quality. Overall, I like to distinguish these three effects for nanoplasmonic antennas that are at work to enhance the signal. The resonance factor, just like a swing, you push it back and forth, you can make the amplitude larger. The lightning rod effect due to sharp corners, and the propagation effect, surface plasmon polariton effect, that naturally focuses these surface plasmon polaritons toward tips and corners. All that contributes to the Purcell factor, directly proportional to the quality factor of the antenna and inversely proportional to the confinement volume of this nanoplasmonic hotspot. Here is another example of an experiment led by Zhe. His picture is at the top. He's now a postdoc at Caltech. In this example, it's an RNA molecule that is being sequenced by the tip-enhanced Raman technique. And at some level, you can say, okay, the tip or the plasmonic nanoantenna works like a lens, a super lens of a sort that allows us to focus light onto the nanoscale as opposed to microscale limited by Abbe diffraction limit. Okay, you can say all that and it's not incorrect, except you need to be careful and you need to remember that it's not only the incoming light that's focused, so to say, into these hotspots, but it's also the vacuum fluctuations through the what's called the Purcell effect. The vacuum fluctuations are enhanced, if you want to use this language, and that contributes to substantial additional enhancement of the Raman signal. What else can we do to enhance this signal even further? How about adding molecular coherence? Kai has talked about it. And we, of course, have used molecular coherence for all sorts of interesting things. What if we drive molecular coherence in these detection and sensing scenarios? Here's my quantum mechanical animation of what a vibrating molecule looks like. When we have an ensemble of these vibrating molecules, we can talk about molecular coherence with all of these molecules oscillating in unison. And molecular coherence leads to interesting, pretty-looking phenomena. Here's a picture of broadband coherent Raman generation, otherwise known as molecular modulation, in a molecular crystal. In detection and sensing scenarios, coherence, this density matrix element, rho BC, the off-diagonal density matrix element, produces orders of magnitude enhancement of coherent Raman signal compared to incoherent, spontaneous Raman. This is what we now call the Scully formula for signal enhancement. And it's this coherence enhancement that allowed us to measure spectroscopic signatures of bacterial spores in real time. We used femtosecond shaped laser pulses and looked at vibrational Raman fingerprints of spores and such. On a single shot basis with a picosecond worth of light, we can get enough signal to detect these molecular fingerprints if we use molecular coherence. And this is an example of combining molecular coherence with the plasmonic enhancement, which the enhancement factors multiply. We achieve a multiplicative enhancement overall, and this is what others have called astonishing result, astonishing sensitivity. I'll move forward, and I'm checking my time. I still have a few minutes, but I don't mind finishing early, especially because Kai has already given such a beautiful introduction to this topic. This is the other type of coherent molecular spectroscopy, driven directly but by infrared excitation as opposed to Raman excitation. Here we drive molecular vibrations directly. Of course, we need to be mindful of selection rules and symmetry, and Kai has given a nice introduction to that. And he has even shown this overall picture of the setup. I'll try to strike and stress some of the points Kai made by supporting them with data from Texas A&M. Kai has talked about how this sum frequency approach is advantageous in many ways, including the advantage of high spatial resolution afforded by visible signal. We drive the molecules by mid-infrared light, and the diffraction limited spot in mid-infrared is of order of several microns. In this particular experiment, it would be 4 microns. And if we were doing mid-infrared spectroscopy and microscopy directly, that would be our limit. With the ITS technique, the sum frequency technique, because we are doing the measurement in the visible frequency range, our spatial resolution is a factor of 5 or so, almost an order of magnitude better, 0.9 micron instead of 4 micron. And Zhizhou Wang and Nathan Marshall did this experiment here at Texas A&M, and they continued forward to apply this coherent vibrational microscopic technique to look at biological samples such as C. elegans worms. These tiny worms, about this big, some people like to call them hydrogen atoms of biology. They're very well studied. They're very basic biological systems. And we are trying to do proof of principle experiments by doing video rate imaging and recording of these tiny worms with chemical sensitivity afforded by coherent vibrational spectroscopy. Our future work may benefit from non-classical light, non-classical probes of molecular vibrations, entangled photon pairs, or squeezed light. That's very interesting. We are still trying to understand what exactly can be done and how exactly we can benefit from these non-classical features. This paper theoretically predicted recently that special entangled time anti-correlated, frequency correlated photon pairs can do a better job driving a Raman transition compared to classical light. We are also implementing squeezed light for Raman, coherent Raman microscopy. And we'll see how all that goes. I want to make sure I finish on time, and this is right about the time for me to finish. I want to thank everyone who has contributed to this work, and I want to thank you guys here in this session for listening.
That's great.
Any questions? Phil, you're here. Thank you for co-organizing this quantum engineering seminar.
Yeah, it's quite good. I just wish we weren't competing against Olga's sessions.
Yeah, Olga has put so much work into this overall laser physics conference and into her seminar #1. And it's hard to compete with her. But again, this is recorded, and hopefully will accumulate more audience looking at our presentations as the time goes.
Okay.
Yeah.
So does anybody else have any questions?
Yeah, I can ask the question.
Go ahead, Kai.
Yeah, it's about this theoretical work from Anatoly.
Yeah, this one.
Right. So wondering which one is using the entangled light.
Yes.
It's for the Raman, but I just don't see how it works. Is like which one is the Raman state? A and C?
Yeah, AC is the Raman transition. And we are driving it in the Raman sense up and down with pump and Stokes. And that's why we want frequency correlation. This is an unusual situation. Typically, from parametric down conversion, you get frequency anti-correlated photons. So it takes a little bit more work to make frequency correlated photons. And yeah, that's kind of what's slowing us down. It's a pretty challenging task to produce this special frequency correlated time anti-correlated photon state.
Oh, I see. Oh, I see.
So I'm not sure what exactly we'll be able to do along these lines, but using squeezed light for stimulated Raman microscopy is a real thing. I hope we will be able to implement it very soon.
Right. I just imagine that if you have the photon pair, right, entanglement photon pair, maybe you want it correlated and to drive this Raman state, and then they have this, the frequency difference between these two photons should be fixed or around this Raman pair.
Yeah, that's exactly what happens. Yeah. Frequency correlation means the difference frequency is fixed.
Yeah, then, but in general, you know, if you have the BBO and you generate this photon pair, usually it's the sum of the energy is fixed, right?
Exactly. Yeah, that's what I have just said.
Mm-hmm.
You're exactly right. So it takes a special configuration, and people have demonstrated that it can be done. In this paper, we have references to experimental schemes where people have demonstrated that this can be done. No fundamental problem here, but a pretty challenging technical problem.
I see. Okay.
Okay, thank you. So I guess we'll conclude. Thank you, everyone. Thank you, Phil.
Thank you.
Do you have
thank you,
something to say, Phil?
Thank you very much.
Yeah, thank you, David. Good to see you.
Yep.
Thank you very much, Alexei.
Yeah, thank you, Masayuki. Thank you, Kai.
Yeah, thank you.
And we'll see you all later.
Yep.
Let's stay in touch.
See ya.